Hi everyone, my name is Lars Rovetter. I'm currently a postdoc at EPFL and I will present joint work with Andy Wiese. And this is about a 2+epsilon approximation algorithm for preemptive weighted flow time on a single machine. So let me explain you this scheduling problem. In here, I draw the time axis on the horizontal, and each of these jobs depicted by a rectangle arrives at some time rj. Further, each job has some processing time pj, and it has a weight wj, which describes how important it is. A schedule can look as follows. We have only a single machine which can process only one job at a time, but the machine is allowed to preempt the jobs. This means it can stop processing one job and resume processing it at a later time. So in this example, the blue job, when it arrives, it is immediately processed. The red job is interrupted because the yellow job arrives and it is much more important. And after the yellow and red jobs are completed, the green job is processed. Once we have such a schedule, we can determine the flow time fj of each job. The flow time, or also called waiting time, describes the time from a job being released until it's completed. And usually this is a metric that we want to minimize. In this setting, we want to minimize the sum of weighted flow times. So we take the sum of all jobs and multiply the weight by the flow time, and this is the objective that we want to minimize. This problem is a classical scheduling problem and has received a lot of attention in literature. It has been studied in numerous variants. For example, one variant that is very relevant here is the online setting, where the jobs are only known to the algorithm once they are released and not upfront. In the online setting, it is known that polylogarithmic guarantees can be achieved on the competitive ratio, but on the other hand, no constant algorithm can be obtained, as shown by Bansal and Chan. Other variants that were studied include the setting with multiple machines, settings where we allow speed augmentation, or where the weights have certain restricted forms. But even the very basic question for what is the best approximation rate that you can get in the single machine offline case has remained largely unresolved for a very long time. And this is also considered one of the most important problems in scheduling. For example, in a classical survey on the most important open questions in scheduling, Schumann and Wöginger listed this among the 10 most important open problems. Let me now give you an overview of what is known about the offline single machine case. So one important breakthrough was achieved by Bansal and Poos, who used very elegant geometric ideas and LP rounding techniques to obtain a log-log-n approximate algorithm. This was then improved by Abhadragag and Kumar, who recently gave the first constant approximation algorithm. And this algorithm is obtained by combining an LP rounding technique, and on the other hand, a novel dynamic programming idea. However, this constant approximation, it was only a very large constant. So this constant is something it was unspecified, but it may be much larger than 10,000. Our contribution in this paper is to bring this constant factor down to only 2+epsilon for every fixed epsilon greater than 0. And our algorithm, it's based on ideas from Bhattacharya and Kumar, but we are able to completely get rid of the LP rounding part, which was one very important source for this large constant. So our algorithm now is only built on dynamic programming. At this point, let me also mention two other relevant related works. One is by Chekuri and Khanna, who gave an approximation scheme with quasi-polynomial running time. And another result is by Feige, Kulkarni, and Lee, who gave a very important reduction, which allows you to turn any algorithm with pseudo-polynomial running time. So the running time depends on the number of input, numbers in the input in a polynomial way. These can be turned into algorithms that are truly polynomial. So that means they depend only polylogarithmically on the numbers in the input. The result by Feige et al., it was, for example, only together with this, the algorithm by Bhattacharya and Kumar, and the algorithm by Chekuri and Khanna, and as well our algorithm give truly polynomial running times. Next, let me give you a different interpretation of the problem. Let us take one row for each job and one column for each unit of time. And further, let us sort the jobs by the release time. So the job that's released first is on top, and the job that's released last is on the bottom. So each square in this picture, it stands for a job and a unit of time that comes after its release time. Now the problem comes down to choosing completion times for each job, because once we have chosen the completion times, we can actually compute in polynomial time a feasible schedule. And so we need to select squares in this picture such that we select a prefix of each row. And the cost of the schedule, it is simply the cost of each square that we select, and this square has a cost of the wj value of the job j of this row. But this still does not completely visualize the problem, because if we had only this, then we would simply take just the first square of each job. So there needs to be some constraint that models that the machine cannot just instantly finish every job. And actually, these constraints, they can be written in a very elegant way. Namely, they correspond to vertical arrays in this picture. So array that starts at some square and then goes to minus infinity. And let us now focus on one of these rays. What does this actually mean? So this ray has some demand on the right-hand side, which we derive from a certain integer programming formulation. And this demand has to be covered with the jobs that the ray intersects with. And a job contributes a value of his pj value if he's not completed by the time that's corresponding to the ray. Or put differently, if one of these blue prefixes intersects with the ray, then we take the pj value of the job into the sum. And we have to select prefixes in a way such that the demand for each of these rays is covered. Here there's a important difference to previous works, because in the work by Batra, Garg, and Kumar, they had a similar problem, but they used arbitrary vertical lines. So it was not necessary that these lines go to minus infinity in the y-axis. They could end somewhere, which makes this problem much more difficult. And we show that actually these constraints have a even simpler structure of the form of these rays. I will now give you an idea of how we solve this kind of problem. And we will start out with a trivial special case. Let's say there's only one column, and we have various squares in this column. Let's further select only those squares corresponding to a certain ratio of wj over pj. You can think of wj as the cost of the square and pj as its use, in the sense of how much it covers for the coverage constraints. In this picture on the left, the gold coins, they depict the cost of each rectangle. So if this is, for example, the optimal solution, then opt budget is 4. We will now construct a very simple greedy solution that is also feasible if opt is feasible, and is only twice as expensive. For that, we will first throw away all squares that are more expensive than opt's total budget. Then we will start from the bottommost square, and we pick these squares until we reach a budget that's greater than opt's budget. So in this case, we take the last square. We are still below opt's budget, so we take the next square. Now we are at a budget of 5, so we are above opt's budget, and we stop. It's not hard to see that this change in the solution from opt to our solution, it retains feasibility, because in some sense we are only shifting opt's budget downwards, and the coverage constraints, they always include lower squares, so it cannot be bad to shift the budget downwards. And since we restrict ourselves to one particular ratio of cost over use, we will cover each ray that opt also covers. And on the other hand, this solution can be at most twice as expensive as opt, because we will pick squares as long as we are below opt, and then we may take one square in addition to that, and this square might again be as costly as opt's budget. So we are at most at 2 times opt's budget. And we can actually, if we round these ratios cost over use, which we can, we will end up with only logarithmically many budgets, and we can guess all of them with a small error in polynomial time. And then having guessed these budgets, we can construct for each ratio, we can construct this greedy solution, and we know that one of these polynomially many guesses will be a feasible solution, and it will be at most twice as expensive as opt. Now, this seems like an overly complicated algorithm for this special case, but it is important when we go to the general case. So first, recall that in the general case, we had to select prefixes of each row. But this prefix constraint, we can replace it by a certain group constraint, where we group the rectangles into exponentially growing groups of squares which grow from left to right. And if you take one square from a group, you have to take all of them. But on the other hand, you don't have to satisfy the prefix constraint. So this, for example, would be a feasible solution here. And you can actually show that with this construction, you lose only a constant factor in the approximation rate. So a solution for the prefix constraint, it gives you a solution for the group constraint and vice versa. And in fact, you can even have the group constraint have this nice hierarchical structure as in this picture, where every group is divided into 2 groups in the next row, or the group in the next row is exactly the same as the group in the previous row. And we can even bring this constant factor that you lose down to a factor of only 1 plus epsilon if we apply a few more technical tricks. And now, if you look at one family of groups which are equal except for vertical shifts, then here again you can apply the same trick from before, and you can essentially construct a polynomial number of guesses for the optimal solution, and one of them will be the correct one. We can do this for each such family. Of course, we cannot guess the complete solution, but each of these parts we could guess. And with more involved ideas, you can extend this to be able to guess larger parts of the solution. Namely, for every unit of time, you look at those groups that intersect with this unit of time, and you can actually guess the correct solution for each such family. And now the general approach, to be put very simply, is we take the optimal solution, we simplify it with tricks similar to this greedy approach. Then we are able to guess various parts of this solution, but only parts. But these parts can then be merged by a dynamic program to recover a complete solution. So to summarize, we obtain a 2+epsilon approximation algorithm for a preemptive weighted sum of flow times on a single machine. It is a very interesting problem whether there exists Peters for this. And this is plausible because we know there is a Q Peters. On the other hand, this factor of 2 that we lose by the greedy approach, it is also the source of the factor of 2 in the only source of this factor of 2 in our algorithm. And at the moment, we do not know how to avoid this. On the other hand, it is also known that you need to allow preemptions. If you do not allow preemptions, then there's no constant approximation. And also, if you have many machines, you can also not get a constant approximation, at least if the number of machines is part of the input. Thank you for tuning in, and I hope to see many of you on this year's STOC, or maybe on another occasion soon.